Hello friends, welcome to my second lecture on symbolic representation of statements. Let us define a Y conditional statement. If P and Q are any two statements, then the compound statement P if and only if Q denoted by P implies and implied by Q is called a biconditional statement, and the connective if and only if is the biconditional connective. So, when we are given two statements P and Q, P implies and implied by Q is called a biconditional statement. Now, let us consider an example. He swims if and only if the water is warm. So, let us consider the statement he swims to be P. Let us say P is he swims and Q is the water is warm. Then he swims if and only if the water is warm can be symbolically represented as P implies and implied by Q. Similarly, sales of houses fall if and only if the interest rate rises. So, let us say let P denote sales of houses fall, and let Q denote the statement the interest rate rises. Then the case sales example sales of houses fall if and only if the interest rate rises can be symbolically represented as P implies and implied by Q. Now, P implies and implied by Q is true when both P and Q are true or both P and Q are false. So, truth table for P implies and implied by Q is if P is T, Q is T. Then P implies and implied by Q is T. When P is true, Q is false, the P implies and implied by Q truth value is false. When P is false, Q is true, then P implies and implied by Q has truth value false, and when P is false, Q is false, the truth value of P implies and implied by Q is true. So, that is T. So, P implies and implied by Q is true when both P and Q are true or both of them are false. Now, let us show that P implies and implied by Q is logically equivalent to P implies Q and Q implies P. So, let us form the truth table. P Q have truth values T T, T F, F T, F F, then P implies and implied by Q. The biconditional statement P implies and implied by Q has truth values for T T T, for T F F, F T F, F F T. Just now we have discussed that if P and Q both have truth values T, then P implies and implied by Q will have truth value T, and its truth value will also be T in the case when P and Q both have truth values F. Otherwise, it is always F. Now, P implies Q, truth value of P implies Q, we know it is only F when P is true, Q is false, otherwise it is always true. So, T T gives T, T F, now you see P is T, Q is F. So, T F gives F and then F T gives T, F F gives T. Similarly, we can write the truth values of Q implies P from here. So, they are T T, F T. Now, we can from these two columns P implies Q, Q implies P, their truth values from their truth values we can find the truth values of P implies Q and Q implies P. So, for T T we get T, F T we get F, T F we get F, and T T gives T. Now, you can see the this column and this column we can compare. So, here we have T, here also we have T, here we have F, here we have F, this is F, this one is also F, and here we have T, here also we have T. So, the truth values of the biconditional statement P implies and implied by Q are same as the truth values of the statement P implies Q and Q implies P. Okay. Now, we can consider another example. P implied and implied, P implies and implied by Q is logically equivalent to P or Q, and P or Q implies P and Q. Okay. So, this is equivalent to this one, P or Q implies P and Q. Okay. Let us see the truth table. P and Q have truth values T T, T F, F T, F F. Okay. Then P implies and implied by Q. Okay. When P and Q both are true, it is T, it is F for T F, okay, or F T, and for F F it is T. Okay. Now, P R Q, okay, P R Q. So, this is T T, we get T here, T F gives T here, F T should give T, not F, this should be T. P and Q, T T gives T, T F gives F, F T gives F, F F gives F. Okay. Then P or Q implies P and Q. Okay. So, implication means whenever P or Q is true and P and Q is false, we will get F, otherwise it is always true. Okay. So, P or Q is true and P and Q is true. Okay. So, implication gives T, and when P or Q is true, P and Q is false, we get F here. Now, this one is T and this one is false. Okay. So, we get F here. So, this should be F, this should be T. Okay. So, P or Q is true, okay, and P and Q is F. Okay. So, P or Q implies P and Q. If it is true and this is false, then the truth value is false. Okay. And here we have P or Q F, P and Q false. So, F F here. So, we get T here. Okay. So, this is not F, this is T. We can also show, now you can see the truth values of P implies and implied by Q are same as the truth values of this implication T T, F F, F F, T T. So, they are logically equivalent. Now, the this equivalence can also be shown, the equivalence of P implies and implied by Q and the implication P or Q implies P and Q can also be proved using algebra of propositions. So, for that let us first show that P implies Q is logically equivalent to not P or Q. Okay. So, these are the truth values of P and Q, okay, T T, T F, F T, F F. Not P will be then have truth values F, F, T, T. Not P or Q will have truth values as not P, F T here. Okay. So, we will have T here, F F means F here, T T is T, T F is T. Okay. Now, P implies Q, P implies Q. So, T T will give T, T F will give F, okay. F T will give T, F F will give T. So, now you can see the P implies Q, these are the truth values T F T T and not P or Q, T F T T. So, they are same. So, they are logically equivalent. Okay. So, P implies Q is logically equivalent to not P or Q. We will use this in order to prove the logical equivalence of P implies and implied by Q and P or Q implies P and Q. Okay. So, let us show that by using algebra of propositions. Now, P implies and implied by Q, okay, is logically equivalent to P implies Q. This we have earlier shown. P implies and implied by Q is logically equivalent to P implies Q and Q implies P. This we have earlier proved. Okay. Now, P implies Q, we have just now shown P implies Q is logically equivalent to not P or Q. Okay. So, we have not P or Q here, and here also we have not Q or P. Okay. Now, let us take use distributive law. Okay. So, this is not P or Q we distribute over minus not Q or P. Okay. So, we have not P or Q and then we are distributing over this one. So, not P or Q and not Q, or not P or Q and P. Okay. So, this is obtained by using distributive law. Okay. and then we have here, okay. So, we are using commutative law here, okay. We are using commutative law here. So, we using commutative law. So, not P and not P or Q we write here, and here also we are using commutative law. So, P and not P or Q. So, commutative law we are using here. Okay. Now, after that what we have here, not P or Q, not P or Q, okay. So, we are again using distributive law. So, not P and not Q and not P, okay, or not Q and Q, okay. And then here we are again using distributive law. So, not P and not P we have here, and then we have or P and Q, okay. So, this is again followed obtained by using distributive law. Okay. Now, not Q and not P we have here, not Q and Q, okay, is false. This we have earlier seen in algebra of propositions. This we earlier have done in the first lecture, okay. So, not Q and Q, okay, is F, and P and not P, okay, P and not P both P and not P both cannot be true. So, we have the truth value F, and then here or P and Q. Now, not Q and not P, okay, not Q and not P. Now, this is not Q and not P, this and F, the truth value is not Q and not P, okay, and here we have truth value of this F and P and Q, okay. This is P and Q, okay. This is again by algebra of propositions. So, P and Q, and then we have not Q and not P, okay. This by complement law, it is not P and P or Q, and this is or P and Q, okay. So, we have here now we use this result, this one, okay. Not P or Q is logically equivalent to P implies Q. So, we have now you can see here this is not P or Q or P and Q. So, we are using that, and this is P or Q implies P and Q, okay. So, this is how we prove the equivalence of P implies and implied by Q and P or Q implies P and Q by using algebra of propositions. Now, negation of compound statements. Negation, let us consider first negation of conjunction. A conjunction P and Q consists of two substatements P and Q, both of which exist simultaneously. Hence, the negation of the conjunction would mean the negation of at least one of the two substatements. Thus, negation of P and Q, okay, negation of P and Q is negation of P or negation of Q. This can be proved by the truth table. So, we can show the logical equivalence of negation of P and Q and negation of P or negation of Q. So, the truth values of P and Q are given in these two columns. Negation of P has truth values F F, T T, and here they are F T F T. Then negation of P or negation of Q, we can write the truth values. So, negation of P or negation of Q. For F F we have F, F T is T, T F is T, T T is T, and then P and Q. So, T T gives T, T F gives F, F T gives F, F F gives F. Okay. Now, negation of P and Q, okay, negation of P and Q gives for T we get F, for F we get T. So, these are F T T T. Okay. Now, you can see this column and this column, okay. Their truth values are same for all possible cases, okay. F F, T T, T T, T T. Okay. So, negation of P and Q is logically equivalent to negation of P or negation of Q. So, at least one of the two statements must have negation. Now, negation of disjunction. A disjunction P or Q consists of two substatements P and Q, which are such that either P or Q or both exist. Okay. Hence, the negation of the disjunction would mean the negation of both P and Q simultaneously. Okay. So, negation of P or Q is logically equivalent to negation of P and negation of Q. So, P Q have these truth values, okay, these truth values. Now, negation of P then will have truth values F, F, T, T, okay. Negation of Q will have truth values F, T, F, T, and negation of P and negation of Q will have truth values for F F F, F T F, T F F, T T T, and then P or Q. P or Q will give truth values T T gives T, T F gives T, F T gives T, F F gives F. Now, we can see negation of P or Q. Negation of P or Q is for T we have F here, okay. So, this is F, this is also F, this is F, and this is T, okay. Now, you can see the truth values of this column and this column, okay. So, negation of P or Q have truth values F F, F T, and negation of P and negation of Q also have the same truth values, okay. So, they are logically equivalent. So, negation of P or Q is logically equivalent to negation of P and negation of Q. Now, negation of a negation of a statement is the statement itself. Equivalently, negation of P is equivalent to P. Let us consider the statement P to be roses are red, okay. Then negation of P is given by roses are not red, okay. Negation of P is negation of P. So, negation of roses are not red describes it is not the case that the roses are red. It is not the case that the roses are not red, or it is false that the roses are not red, okay, which is same as roses are red. So, negation of P is same as P, it is logically equivalent to P. Now, negation of implication. If P and Q are two statements, then negation of P implies Q is logically equivalent to P and not Q, okay. So, to prove this equivalence, we prepare the truth table. So, these are the truth values of P and Q, okay. Not Q have truth values F T, F T, P implies Q have truth values T, F, T, T, okay, and not P implies Q have truth values F, T, F, F, okay. Then P and not Q, let us consider this P and this is not Q, okay. So, P and not Q. So, T and F is F, okay. T and T is T, F and F is F, F and T is F, okay. Now, you can see the truth values of P and not Q and not of P implies Q, they are same, okay. F F, T T, F F, F F, okay. So, negation of P implies Q is logically equivalent to P and not Q. Now, let us write the negation of these statements. If it is raining, then the game is cancelled. So, let us say let P denote the statement it is raining, and Q denote the statement the game is cancelled. Then the given statement can be described symbolically as P implies Q, okay. If P, then Q. Now, let us see the negation of P implies Q. We have just now seen negation of P implies Q is P and not Q, okay. So, negation of okay. So, P and not Q means it is raining and the game is not cancelled. Okay. So, P is it is raining, this symbol represents end, logical connective, this is end, not Q, Q is the game is cancelled, not Q is the game is not cancelled. So, it is raining and the game is not cancelled. Similarly, the negation of the second statement we can write let us say P denote the statement he studies, and Q denote the statement he will pass the examination. Then the given statement can be written as P implies Q. Okay. So, negation of P implies Q will again will be logically equivalent to P and not Q. Okay. So, P and not Q means he studies and he will not pass the examination. He will not pass the examination. So, this is the negation of the second statement. Now, negation of Y conditional. If P and Q are two statements, negation of P implies and implied by Q is logically equivalent to P implies and implied by not Q. It is also logically equivalent to not P implies and implied by Q. Okay. So, let us prove the above equivalence. So, these are the truth values of P and Q. T T, T F, F T, F F, not P has truth values F F, T T, not Q have truth values F T, F T, P implies and implied by Q. We know P implies and implied by Q has truth value T if both P and Q are true or both of them are false. Okay. So, T T gives T, T F gives F, F T gives F, F F gives T. Okay. And not P implies and implied by Q. Okay. So, negation of P implies and implied by Q will then have truth values F, T, T, F. Okay. P implies and implied by negation of Q. Okay. So, this is P. Okay. Negation of Q is this one. Okay. So, T F gives F and here T T gives T. Okay. Then F F gives T. Okay. And F T gives F. Okay. Similarly, negation of P implies and implied by Q, this is negation of P and we have Q here. So, F here, T here. Okay. So, we get F here, then F here and F here. So, we get T here. Okay. Then T here, T here. So, we get T here, T here, F here. So, we get F here. Now, you can see the truth values of negation of P implies Q, they are F T, T F and here F T T F. And here also F T T F. Okay. So, negation of P implies and implied by Q is equivalent to P implies and implied by not Q, which is logically equivalent to also logically equivalent to not P implies and implied by Q. Now, negation of P, we can also note this, negation of P implies and implied by Q is negation of P implies Q and Q implies P. We have already shown that P implies and implied by Q is logically equivalent to P implies Q and Q implies P. So, we can put that equivalence here. So, P implies Q and Q implies P. Now, negation of P implies Q we have seen, this is logically equivalent to negation of P or Q, and Q implies P similarly is equivalent to negation of Q or P. Okay. So, we have this much negation of P or Q. Okay. When we take, now let us use complement law. So, negation of this and this will be negation of this or negation of this. So, negation of not P or Q or negation of not Q or P. So, this here we are using complement law. Okay. So, then negation of P or Q, then again by complementary law becomes P and negation of Q, and the negation of Q or P again by using complement law gives Q and negation of P. Okay. So, this also comes by negation complement law. So, negation of P implies implied by Q is logically equivalent to P and negation of Q or Q and negation of P. Now, let us write the negation of the following statement. He swims if and only if the water is warm. Okay. So, let us say let P denote he swims. Okay. and Q denote the water is warm. Then the given statement can be expressed as P implies and implied by Q. Okay. He swims if and only if the water is warm. Now, negation of P implies and implied by Q we can write, we go to this one. Negation of P implies and implied by Q is P implied and implied by negation of Q. So, let us write okay. P implies and implied by Q is logically equivalent to P implies and implied by negation of Q, and this is logically equivalent to negation of P implies and implied by negation of P and implies and implied by Q. Okay. So, we can say okay, first we can use this equivalence, this one. Okay. So, P implies and implied by negation of Q. So, he swims if and only if I am using this equivalence. So, he swims if and only if the water is not warm. And if I use this equivalence, P implies and implied by Q is logically equivalent to not P implies and implied by Q, then we will get the following: he does not swim if and only if the water is warm. So, negation of the given statement can be one of these two, any one of these two. He swims if and only if the water is not warm, or he does not swim if and only if the water is warm. Okay. Similarly, let us say for the second statement, okay, let us say let P denote this computer program is correct. This computer program is correct, and Q denote the statement it produces the correct answer for all possible cases sets of input data. Okay. Then the given statement in the case B is can be expressed as P implies and implied by Q. Okay. So, negation of P implies and implied by Q will be then logically equivalent to P implied and implied by negation of Q. Okay. And negation of P implied and implied by Q. Okay. So, again if we want to write the negation of P implies and implied by Q, it could be either of these two, P implies and implied by not Q or not P implies and implied by Q. So, if I use this one, this equivalence, P implies and implied by not Q, then P implies and implied by not Q will be giving us the statement this computer program is correct if and only if it does not produce the correct answer for all possible sets of data. Okay. And if I use this one, then I will say not P. So, this program is not correct if and only if it produces the correct answer for all possible sets of input data. So, we can easily say that. So, let us now consider derived connective NAND. It means negation of conjunction of two statements. Now, we have already defined conjunction of two statements. If P and Q are two propositions, then NAND of P and Q is a proposition which is false when both P and Q are true. When both P and Q are true, then none of P and Q is false, otherwise it is always true, okay, and we denote it by this symbol. Okay. So, P non Q. Okay. So, none of P and Q is logically equivalent to negation of P and Q. Okay. So, this is truth values of P and Q. Okay. These are truth values of P and Q. So, none of P and Q, when P and Q both are true, then its value is false, otherwise it is always true. So, in all other cases it is true. Okay. Now, let us prove the logical equivalence of none of P and Q and negation of P and Q. So, let us write the truth values for P and Q. Okay. So, for T T we get T, T F is F, okay, F T is F and F F is F. Okay. So, negation of P and Q. So, negation of T is F, for F we write T here. So, you can see the truth values of non P and Q, they are F T T T, okay, and here also they are F T T T. So, this is they are logically equivalent. So, let us now discuss the derived connective NOR. It means negation of disjunction of statements. Disjunction of statements we have already discussed. Let P and Q be two propositions, then NOR of P and Q is a proposition which is true when both P and Q are false, otherwise false. So, when P and Q both are false, okay, then P NOR of P and Q is true, okay, otherwise it is always false. So, in all other three cases its value, truth value is false. Now, we have to show that NOR of P and Q is logically equivalent to negation of P R Q. Okay. So, let us write P R Q here. So, for T T we have T, T F means T, okay, F T means T, F F means F, okay, and negation of P R Q then gives you F, F, F and T. Okay. So, these truth values are same as the truth values of NOR P and Q. So, they are logically equivalent. Now, let us note that negation of P is logically equivalent to NOR of P and Q. We can easily show this. So, let us show that not P is logically equivalent to NOR P P. Okay. So, P has truth values T and F, not P has truth values F T, okay, and P NOR P P, okay, NOR P P. Okay. So, when they are both T, okay, then NOR P P has truth value F, okay. So, this case will be F. When it is F F, okay, then we will have T, okay. So, they are same, okay. So, they are logically equivalent. Now, similarly, let us now consider the third case, exclusive OR. So, let P and Q be two propositions, then exclusive OR, which we also write as XOR of P and Q denoted by this symbol, okay, is the proposition that is true when exactly one of P and Q is true, but not both, okay, and is false otherwise. So, the truth table for exclusive OR is exclusive OR P Q is the proposition that is true when exactly one of P and Q is true. So, P is true, Q is false, then P exclusive P Q is true, here also when it is F, it is T, it is true, and then it is false otherwise. So, when exactly one of the two P R Q is true, then its value is true, otherwise it is false. So, for T T it is false, for F F also it is false. Okay. So, this is the case exclusive OR, which we also write as XOR, okay. And the properties of XOR are XOR P and Q, XOR P Q is same as XOR P Q P, and then it also follows the associative law, it also follows the distributive law. We can see the first case. So, P Q, let us say P Q, they have truth values T T, T F, then F T and then we have f f. Okay. So, then we can write the truth values for XOR P q. Okay. So, we have seen that T t gives f, okay, T f f t gives T t, and f f gives f. Okay. So, either one T or f, okay, P or Q should be true. Okay. So, then Q P. Okay. So, again for Q is true and P true, okay, we have f here. For Q false and P true, it is true here, okay, and then for Q true and f false, P false, it is true here, and then for Q f and P f, it is again f here. Okay. So, the truth values of XOR P q and Q p are same. Okay. So, they are logically equivalent. Okay. So, this is the proof of the first property. Similarly, we can show the proof of the associative property and the distributive property. This is the third case here, exclusive OR in the derived connectives. So, with that we come to the end of this lecture. Thank you very much for your attention.